Hello, my name is Temirlan Galimjanov. I am a research assistant in the Tactile Robotics Laboratory of Nazarbayev University. I'll present our work entitled Linear Negative Stiffness Honeycomb Actuator with Integrated Force Sensing. This slide briefly explains the variable impedance actuation concept. Variable impedance actuators have nonlinear stiffness elements located between an actuator and the link of a robot. These elements can be tuned to provide variable stiffness. Schematic representation of variable impedance actuation concept can be seen in the figure in this slide. Additionally, it shows several examples of benefits using such actuators like safety, energy, efficiency, and dynamic adaptation. Brief description of negative stiffness honeycombs is presented in this slide. Negative stiffness honeycombs consist of negative stiffness beams. Negative stiffness beams might be assembled in 2 dimensions or 3 dimensions. Negative stiffness honeycombs are considered as metamaterials due to their unusual characteristics. One of those characteristics is presented in a graph. This graph shows the force displacement dependency of the beam. If we look at this graph, we can easily observe non-linearity with negative slope in some region. These features allows us to use those beams to design complicated structures as NSH with extraordinary properties. 2 figures in the bottom shows the representation of negative stiffness honeycomb and traditional honeycomb. This slide illustrates the motivation of our research and problems which we face. Also, the slide describes our proposed solution. The main motivation of this work was a design of a variable impedance actuator. Also, we wanted to replace traditional positive stiffness elements in actuation with negative ones, because positive stiffness elements have limited shock absorption and energy storage capabilities, which may be dangerous to people and might be a reason of actuator crash. On our way of research, we faced challenges like manufacturing robust variable impedance actuator system designed with integrated negative stiffness elements. Another problem was the designing of appropriate sensors for variable impedance actuators integrated with the negative stiffness materials. The solution for described problems is the following. We propose using negative stiffness honeycomb as nonlinear elements in variable impedance actuator robots. Also, we implemented force and compression estimation sensing system with use of magnetic sensors. These decisions allow us to track force and position of variable impedance actuator with high precision in a real-time stiffness changing. In this slide, assembled setup can be observed. It includes the linear actuator with its controller, dynamic cell motors, and the negative stiffness honeycomb with integrated magnets and magnetic sensors on it. Also, the setup contains load sensor and the national instrument connector block. Figures in the right shows closed loop to the sensing system. It is mounted to the honeycomb and consists of 4 magnets located in front of 4 magnetic field sensors. The setup was assembled on top of an optical breadboard. Here you can see the hardware block diagram of the system. Each element of the system is represented with the colored box and the signals are represented as the arrows. In this diagram, we can see the dynamic cell motors, magnetic sensors, motor driver and the load sensor are powered with power supply. Also, we can observe that linear actuator sends feedback to the data acquisition card through its motor driver. Similarly, measurements from magnetic sensors and the load sensor come to the data acquisition card. Then all this data goes to the computer and processed in the implemented PID closed loop control system in C code. Finally, the resulting output values are sent to the dynamic cell motors and the linear actuator as the position. This slide shows the previous hardware block diagram of the system, but in this case it provides a detailed description of the elements of the system. This slide explains the buckling theory. Also, it illustrates two figures. Figure A shows two equilibrium states of buckled beam and figure B shows beams stacked to create NSH. As you can see in figure A, if axial force F with subscript A exceeds beam's buckling capacity, then beam buckles. In the first state, beam resists the deformation force perpendicular to its axis. If a force F exceeds a certain limit, then the beam jumps to its second state. In this slide, you can see the NSH modeling overview. The slide shows the equation with determined variables which are used in beam modeling. Also, this slide shows the plots obtained from the presented equations. Figure illustrates the generated plots which show the changes of force, potential energy, and stiffness with change in d. Presented figure shows the characteristics for three types of beams. They are metastable when beta is equal to 4, critically stable with beta equal to 8, and bistable with beta equal to 12. If the force values has local minimum exceeding boundary condition, then the beam considered as bistable. We can observe it in the top right corner of the figure. The data of bistable beam is colored in red and it has negative local minimum outside the boundary condition. This slide continues the previous slide, but in this case it has the illustration of graphs generated for combined beams. Two plots show the force displacement characteristics for parallel and series combination of the NSH. Both combinations have two beams. The net force for all combinations can be found by summation of all forces generated by beams. When the beams are assembled in parallel, we can get force displacement characteristic by simply adding all force displacement values of each beam. This is valid until one of the beams reaches its limit. Let us now consider series combination of beams with different stiffness values. All beams will have different displacement, that is why we need to consider it while plotting force displacement characteristics. In this slide, we show the schematic drawing of NSH and provide the dimensions which were evaluated for our purposes. The material that we used to print the negative stiffness honeycomb is polylactide. The height of the middle section of the beam thickness, beam depth, and the beam length are the adjustable parameters. They are tuned to achieve appropriate behavior of the overall system. This slide shows our very first experiment in this work. This experiment was conducted in order to extract force displacement characteristics. The scenario of the experiment was simple compression of the negative stiffness honeycomb with the linear actuator and recording data from the load sensor. The figure shows the force displacement characteristic obtained theoretically and empirically. We obtained force thresholds for each of 4 beams. The results are presented in this slide. First figure in the slide shows the output of magnetic sensors as the voltage. As a result, we can measure overall force and displacement by switching between sensors. It implies that we use different magnetic sensors data for different force values applied. The figures on the right shows the result of our second part of this experiment. In this part, we estimated force and displacement and compared it to real values. As we can see, the precision is pretty well, because the slopes of the graphs are close to 1. This slide shows the experiment where we designed a closed-loop control. In the beginning, we used the load sensor measurements as an input to ensure the ability of the system to operate in real time. Then we replaced load sensor values with magnetic sensor measurements and conducted experiments again. There were step force reference and sinusoidal force reference experiments. This slide shows a video demonstration of conducted closed-loop experiments. In the experiment 1, sinusoidal input with increasing amplitude was addressed to the linear actuator. It means that target position of the linear actuator is sinusoidal with increasing amplitude. Now you can see how the actuator behaved during the experiment 1. In the graph in the bottom we can see the data plotted in real time. In the left hand side figure, blue line is the estimated force and green line represents actual force exerted by a system during the time. In the figure on the right we can see position values changed with the time. Experiment 2 shows demonstration of the setup while tracking constant force. You can see how actuator rapidly goes to the desired position with a small overshoot and system tries to keep this position. In the first graph, red line corresponds to the set point force and the blue line represents the estimated force during the time. The desired position values are in the right hand side colored green, and this line is the result of closed loop control system. Experiment 3 is the last one. In this experiment we combined concepts of previous two experiments. We did sinusoidal force reference tracking with increasing amplitude. In the video you can see how actuator goes to the initial position from zero value and then changes its position in order to follow desired sinusoidal values of force. In the left figure you can see the set point force colored red and desired force colored blue, and green line corresponds to actual force measurements from the load sensor. To conclude this presentation, let me mention that our work proposes the first use of NSH variable impedance actuation systems. Also, we integrated magnets to the NSH as sensing elements. Experimental results prove the feasibility of proposed actuation and sensing concept. Thank you for your attention.